Okay, Bismillahirrahmanirrahim. Let's start this lecture. Today we are going to solve one problem from the design of shafts. In the class we have already discussed about the basis of the design, and in this lecture too we'll also revise some of these bases or standards which we have to use while designing of shafts. Before starting the solution of the problem, I just want to mention that there's also one solved example uploaded on the classroom, and that problem is typically related to the two pulley system. So today we will discuss a problem in which we have one pulley and one gear system. So as we have discussed in the class, there could be three power transmitting elements that can be mounted on a shaft, especially for this course. But in practice, we can mount number of elements like clutches, like flywheels, and all these things, sprockets, gears. So in this particular problem or in this particular course, Design of Machine Element 1, we are going to analyze three power transmitting elements. The one is the belt pulley system, the second one is the gear system, and third one is the chain sprocket system. And because this problem only contains gear and the pulley, but during the solution of the problem, I will also discuss that if we replace the pulley by the chain sprocket, how you have to analyze this power transmitting element, that is chain sprocket system. So let's start with the our solution. So because of the lack of time, I will only discuss the solution of one problem, but I will also during this lecture I also mention the variation that could be possible in those in the problems, and that could be the part of your final exams. So let's start with the problem that we're going to solve in this class, and that is the problem statement. So the problem statement states design a step shaft according to ASME code. Now, as we have seen in the slides, there is a specific ASME code for design of shaft, and when we go towards the solution of the problem, we will also show you these particular ASME codes. And the layout is given. Whenever the problem will be given in exam, the layout clearly will be given in the exam. So you know with the diagram that how the elements are mounted on the shaft and what are the supporting bearings and what is the location of those bearings. So shaft is machined from AISI 1144 steel. It is also called 44 steel. This is one of the most commonly used steel material that is for shafts. And as I have discussed in the class, that the steel used for manufacturing of shafts generally have the high, you can say, hardness, and it has a high yield and tensile strength. As you can see, its yield strength is about 573 megapascal, which if you compare with the standard steel, which is mild steel is around 300. So this is almost this yield strength of this steel, that is AISI 1144 steel, has almost a double of yield strength as compared to the normal structural steel, which is mild steel. So generally the steel used for shafts are generally have a very high yield strength and has a high toughness as well. Okay, so this shaft material has a yield strength of 573 megapascal and an ultimate strength of 814 megapascal. You also select these materials from the tables. If you like, I also mentioned in the class that you can also use AISI 1045 steel, which is also another very common type of steel. So just mention here AISI 1045 steel. This is again very commonly used steel material, shaft material, but AISI 1144 is also a very common shaft material. The shaft receives 20 horsepower at 250 RPM from a generator through a wheel belt drive with the pulley. So what happens in these power transmitting elements, there is a one element that receives the power and the other elements used to transmit that power to another, like just give an example. So let's say your car engine generates a power. That power is actually transmitted through gear, so through gearbox and to the wheels. So you can say one is a power generating source, second is a power consuming source, or sorry, power consuming component. So in case of cars, your engine is a power producing source, and while controlling the speed you use gearboxes. This gearbox contains a number of gears, and then you actually enhance the torque and all these things to actually transmit this ultimately to the wheels. So similarly in this case too, we have a generator. That generator is directly coupled, or whatever you can say, either from a motor or whatever you call it. So generally generators generally produce electricity, but you can also replace it, let's say call it a motor, for example, just in case, just to make it more realistic. So let's say we have a motor with 20 horsepower running at 250 rpm. It actually power is inserted into a shaft through this pulley belt system, which is V-wheel drive, and deliver power to a blower system at the gear. So there is certain blower here, which is, you can say there is a one step gear, and there's a blower. Blower could be a radial fan, or used like in cement plant we have a huge blower that actually lifts the dust about 100 feet, so it spreads over the wider area, like almost a 5 square kilometer area, so that the dust density within that cement environment become reduced. So these are and there are other blower systems also used in different industrial systems. So we have a blower. Now we can see the power is entering into the shaft. So this is the gray is your shaft. This is the shaft with the one diameter, and it delivers power to blower system. So you can say blower system is attached at this point. So we have a blower here, and in this case it is also draw load, shear force and bending moment diagram. By the way, in your exams it's not necessarily that you have to draw the shear force and bending moment diagrams, but yes, load diagrams are important, because without the load diagrams you cannot analyze and you cannot design this shaft. So I think it's clear from the problem that you have to design a shaft, and step shaft generally means so problem can come in two ways in the exam. Either you have to design a step shaft, or it is written design a shaft. So what is the difference between these two, I will elaborate at the end of this lecture. Okay, so let's start with the problem. So okay, let's before starting a problem, I'll just give you a little variation. There could be a possibility that there is another element located here, for example a chain sprocket system, which is also consuming power. So now it's become difficult. So let's say we are receiving 20 horsepower, and there is certain amount of power which is consumed at the gear, and certain amount of power that is consumed at the chain sprocket. Those particular problems, in problem it is given like 40% of the power, let's say, is consumed by the chain sprocket, and definitely the sprocket will be attached to any load, like probably some pump or whatever that is, which this is not a concern. But the problem, so if we have one element that receives the power on the shaft, and two elements are actually using that power, and that is quite common in cars. For example, whenever you can say it's a crankshaft that generates power. When crankshaft come out of the assembly, so there is a sprocket. This sprocket is called timing sprocket, and that sprocket is used to connect between camshaft and crankshaft. There is a belt, so there is a chain, and there is a sprocket here. Extending that, we have two pulleys. Generally, in some cars we have one pulley, but in most of the cars we have double pulley system. Generally, one pulley is attached with the generator or alternator of the car, and other pulley is attached, in most of the cases, to the AC compressor, or in some cases the steering power pump. See, now this is a one, so you can say power is generated by one shaft, but consumption are some power consumed by the, let's say, and also this power is also transmitted to the wheels as well. See, we have generation source is one, but we have number of elements that are consuming those power. In those particular cases, we need to know that what is the percentage of, or how many power is consumed, how much power is consumed by one particular function. Like cam is actually operating the valve, so it's consuming certain amount of power. Similarly, you have an alternator through a belt drive system is also consuming some power. You have an AC compressor and a steam power pump. It's also consuming some power, and your wheels that have to run the car on the road, they're also consuming power. So in those particular, although the problem will be not as complex in exam as in case of the cars, but there could be one element that is consuming the power, so that is seeing the power of the shaft, and there could be two elements that are delivering those power. So when those problems will be given in the exam, so in the problem it is clearly mentioned that how much power is consumed by one element. So for example, if it is written that only 40% of power is consumed by the chain sprocket system, so you definitely know the rest of 60% will be consumed by the gear system. So this is definite. And now in this particular problem, there is no such mention, which means that 100% power is consumed by the gear. So that actually simplifies the problem, and see how this actually simplifies the problem. So before starting the problem, we first have to find the allowable shear stresses, and as per ASME code, which is also given in the exam, that 0.3 of sigma y or tau allowable is equals to 0.18 of sigma u, and we have to use whichever is less. So 0.3 of, what is sigma y? It's 573. So value comes out to be 171.9 megapascal. Similarly, 0.18 times, and the ultimate tensile strength or ultimate strength is 814, and the answer is 146.5. See, this is our designed value. So whichever value is less in both of the cases, we have to select that particular value. Now, in the next step, we have to analyze the forces, and before analyze those forces, first of all, just find the torque on the pulley. So torque is a prime parameter in those particular problems. So torque, so we know from power is equals to, so we know power is equals to 2 pi n t by 60. So from that we know T is equals to 60 P over 2 pi n. We know from our previous knowledge. So 60 into the power is 20 horsepower, but horsepower is a British unit. So we convert it to SI units. So 20 into 746. You know 1 horsepower is 746 watt. Divided by 2 into pi, and RPM is mentioned in the problem, that is 250. So shaft power is because it is mounted on the same shaft. So both the elements, the pulley and the gear, they have the same RPM. So calculating it, we get a value of 570.2 Newton meter. Okay, so now in this particular, if you look at the diagram, we have two bearings, bearing 1, bearing 2, and we call this location as like G. This is called as at B1, this is called at P, and this location called as B2. So bearings are the support elements. They do not have the power, either the power transmitting or power consuming elements. They are only used to support the shaft or any static structure. So they are important because if you do not place these bearings properly, your shaft will wobble or vibrate. So it's very important to place these bearings. but in these particular problems in the exam, the bearing location will be well defined in the diagrams. So the first important thing is try to analyze those forces. So let's just start with the pulley. So pulley has, so this is actually you can say this is your front view, and this is your side view. This is the front view of the figure, and this is the side view of the figure. So see, this actually, this side is inward. How we know that? Generally, you can't exactly determine, but you can say, what you can say is that would probably be also mentioned in the or in other words, you can actually check with the you can say the direction of the rotation of shaft. So for example, if the rotation of shaft is in the anti-clockwise direction, and this direction is also, so see, this is this is clockwise, so this must be, yes, this must be inward. Clear? So you can also see with the help of the rotation of the shaft, the rotation direction also given on the elements, you will exactly see what either they're inward or outward. Actually this affects the direction of forces. So by seeing the direction of the shaft, or direction of the rotation of shaft and the direction of rotation of these elements, you can actually determine where they are located. Now in case of the pulleys, we could have different scenarios. The pulley, the direction of pulley, let's say pulley is moving this direction. So this is, we have called it as F1, we call this as F2. Generally the direction, this is called the tight side of the pulley, and it's called the slack side of the pulley. Sorry, belt, not pulley, sorry, belt. So F1 is called, and F1 generally the rotation will, this is generally will stretch the belt, because this will actually, the pulley is moving this direction, so it will stretch the belt here. So we have a tight side on this side. So based on this, we have to find the bending force on the pulley, and that bending force on the pulley, that bending force generated by the pulley, sorry, is actually directly transferred to as a bending forces on the shaft. So if okay, let's start with the pulley. So we have a pulley, we have a pulley system here. So in the diagram we say its angle is, this angle is 45 degrees, and then this is F1, this is F2. Again, this is determined by the direction of force. The direction will determine this is, you can see, this is your tight side and this is your slack side. But remember, the tension, this is F1, F2 are tension on the belts. The F1 is the tension on the tight side of the belt, F2 is the tension on the slack side of the belt, but they are actually in this direction. Clear? Always in the direction away from the pulley. So the total force on the pulley, total bending force on the pulley, is actually the sum of two forces. The sum of F1 and F2. The total bending force which is actually required to design the shaft is actually equals to F1 plus F2. F1 is, again I am repeating, it's the tension on the tight side of the pulley, and F2 is the tension on the slack side of the pulley. Now if the power is given, it's very easy to find these bending forces, and we will see in the problem. But like the problem I have uploaded in the classroom, the power is not given in that particular problem. In those particular cases, you have to find the torque, because power is not required, the requirement is torque. So if you find out the power from torque, it's fine, but actually we require torque to find the forces on these elements. Now torque, if power is directly given in the problem, you can find the torque as I've done in this step. But like the problem I have uploaded and the solution is uploaded, the power is not given. Rather, the tight side force is given. So see, if you look at the problem I've uploaded, which is not the case in this problem, but just give you an elaboration that in some cases power is not given all the time. So say F1 is given, which is some certain value, like I think it's 2.25 kilonewton. I think I just remember that, but just give an idea. So we don't know all the other forces, but in those particular problems, we know the other two things. One is the wrap angle, which is the angle that the belt is in contact with the pulley. That is called the wrap angle, and the other is called the mu, which is a friction coefficient between belt and the pulley. So we use the formula 2.3 log of F1 over F2 equals to mu theta, and so the formula is given as I think F1 over F2, this also valid, is e power mu theta. This also valid. Both are the same formulas. Clear? Okay. So so in the particular problem, F1 is given, F2 is not given, but the mu and theta is given. From that particular problem, you find F2 because it's very easy to find. You know F1 value, which is given the problem. You know mu, you know theta. Just solve this, you get F2. From F2, the torque can be estimated as, just remember, the torque will be F over D by 2. But in case of belts, it's a difference of two forces. Clear? So only if you know F1 and F2, only then you will be able to find the torque. This is in the case when the power is not given. So then you have to find the torque, because ultimately torque is a requirement. Now if in the exam or in the problem the power is given, there is no need to go through all these grinding, because already you know the torque on the pulley. Now there are certain relations in case of V belt, and it is given in the problem exams too, that the F1 in case of V belts, the F1 is generally 5 times F2. So you can say tension on the slack tight side is almost 5 times the tension on the slack side. Okay, now I just need to find just draw forces here. So what you have to do is try to draw all these forces. Here, just allow me to quit the program and I will run it again. Okay, just I start from the previous. Okay. Okay, what you have to do, I've already actually have drawn it, but exam you have to do it yourself. First you have to draw the forces. So here we have, so if this angle is 45 degree, you can also say that the angle, this angle is also 45 degrees. Clear? So see, we can say that this force, okay, allow me to open it again. Okay, so we have bending forces here, bending force here. So it has two components because it is at an angle of 45. We have one component that is called FBH. We call it as FBH, which means horizontal belt force, and then another component which is down here, or just from different colors so you can see easily. One is component is here, that is called FBV. Clear? Now here we will find the forces. Now look at the gear. Now in the gear we have to find the forces, and in the problem only spur gear will be given. So gear has two forces. It has the radial force, it has the tangential force. Clear? Tangential force is generally used to drive the gear, and radial force is actually applied inward to the shaft. So that is actually a main there is actually there is the main load that actually is responsible for the bending of shaft, but the tangential load is also very important in gears. So if we have this, if direction of gear is this, so and we have two meshed gears, the normal force, which is W1, is applied in this direction. So there is a reaction force in this direction, and always remember you have to draw the components for the reaction force, not the action force in the gears. Always remember, because you have two meshed gears. So because the force is the main gear direction is actually in the clockwise direction, so apply a force like this. The driven gear then apply a reaction force. So just draw it here. So we have called Wn. This is the reaction force. It has two components. One component is towards the shaft, which is we call at Wr, and second component is generally we call it as Wt, the tangential component. You see this component actually responsible for the driving of the gear. Yeah, this component is responsible for the driving of the gear. So the angle between this is called the angle between normal force and the tangential force is called the pressure angle of the gear, that will be denoted by phi. And again repeating, the angle between the normal force that is applied directly, or like if you want to understand, so if we have one tooth here and one tooth meshed here, sorry, so because this is at an angle, so the force applied is at an angle. Clear? And that angle is actually the pressure angle of the gear. Clear? So the pressure between normal force and tangential force is the pressure angle of the gear. So see, we have also two forces. One is the radial force, and tangential force. So we have also two forces on the. So when we draw on the vertical plane, see on the vertical, if you just draw two triangles. So this is again this is FB. We have FBH, and this is FBV. The angle is 45 degrees. Clear? Now we have split FB, which is a bending force because of the belt pulley system, and we have actually two forces, that is WR and WT. WR is the radial force of the gear, WN is the normal force, and WT is the tangential force. Because WR and WT are the important forces that are applied on the gear. The components, WR is the vertical component, W is the horizontal component. So when we draw on the vertical plane, so this is the vertical plane. Clear? So in vertical plane, just for instant, just forget about these forces. For forces, just forget about these. You see, see, this is also in the upper direction. This is also in the upper direction. You see, in both these cases, we have WR and FBV in the upward direction. This is again very important, that you have to actually draw correct direction of the applied force. Clear? So see, when we actually, and again I am repeating, this is the reaction force triangle. Always remember, in gears you have to draw the triangle for the reaction force, not the action force. So see, that's why the direction of normal force is in this direction, because that the force that is towards the so see, this force is away from the shaft. Now this actually does not cause the bending. The reaction force that is actually applied because of this force actually is towards the shaft. See, this is actually towards the shaft. That is actually responsible for producing bending in the shaft. So that's why the reaction normal force is actually a key force that we have to take on to analyze the forces on the shaft. So we have two components. One is the radial component, upward component, and second is the tangential component, which is in this direction. Okay, I see both these forces in the same direction, and we have applied this. Now the two bearings. So bearing has two reactions. One is the horizontal and one is the vertical. Now the direction is you do not have to worry about direction. You can draw any direction. Just give a guess, and the reaction is a negative direction, which generally means that you know from mechanics of material theory that if the reactions are in the opposite direction, you have to actually reverse the direction of those reactions. So because bearings actually are support elements, they only give reactions. Like you are studying in the mechanics of material theory, like simply supported all these things. This is also the bearing also considered as the supports. There are two reactions. One is the horizontal, one is the vertical. So see, we have applied a horizontal. Just rub it. So we have two reactions. One. So just for a good guess, I brought in this direction, because it certainly seems that if the applied forces are in the upward direction, there must be a reaction in the opposite direction. Similarly, if you look at other two forces, like this is the force in this direction, horizontal force, and the bending force is also in this horizontal. So see, both are in the same direction, and again we applied both these forces in the same direction. Now again, you can also draw it like this. There is no problem. In those particular direction will be opposite. See, so do not confuse with these directions. Do not confuse these directions. There are any, but what you have to see is the relative direction. So if the tangential component in this direction, so it must in this case the belt force is also in the same direction. So you have applied the same direction for both, either upward, either downward. Let's say if the same pulley has a belt, let's say here. For example, instead of belt here, we have a belt here. So now we have one horizontal component here, vertical. So vertical component is still there, but horizontal component is now in the opposite. So see, the gear has the WT in this direction, but now the horizontal component is in the opposite direction. So when you draw it with the WT in this direction and F like in this direction. Just to give you an idea. So in this particular case, because both are in the same direction, you have to apply in the horizontal plane. We have to actually draw same force in both forces are in the same direction. Either you can draw both upward, you can both draw downward. But as a symbol, let's say if I take upward as positive, and also in this case vertical is upward as positive, then there is also we can take up, and other is taken as downward. So reactions are, again I'm repeating, there is no problem if the reactions are coming negative, reverse the direction of those reactions. Now whenever you have done this, now in the exam there is no need to draw this three-body diagram, the first diagram, this, but there is marks for these diagrams. This is called load diagrams in both planes. So this is important and carries marks. So please draw these diagrams. If you draw the first 3D diagram, and that will help you, that you can draw it, and that will help you to find analyze all these forces. But it's up to you. If you don't want to draw it, no problem, but the load diagrams are important, they carry marks. Now the next step is to find all these forces. Now we know the locations. Now these element location are known. See, 10 centimeter, 20 centimeter, 15 centimeter, and the diameters of all these elements are known. Like this crossbar dia, the diameter of 25 centimeter, pulley the diameter of 35 centimeter. So these are known. So now the next step is to quantify those forces. So we have drawn these forces, we know the location of these forces, we have drawn the distances between these forces, we know from the location of the bearings and the materials. And again I'm repeating, the bearings, where the bearings are located, they give reactions, and where the elements are located, power transmitting element, they give actions, like the load forces or the bending forces. Now the first step is to find the action forces, which is the element forces. Now in case of first we have to find FB, which is the bending force of the belt pulley system. Is generally, in case of belt system, this is found out to be 1.5 times Fn. If we know the driving force of the belt, we can find the bending force on the belt. And again I am repeating as in the last slide, that if the load, if the power is given, the torque is regulated, there is no need to go through this series of formulas. But if the torque is not given, and you know the one of the tension on the belt, then you can find the torque based on the tension. But if you do not have any tension, if the tension is not given, even the tie and slack side, and the torque is also not given, so it's difficult to then find the torque. So in the problem, either power is given, so from power you can find the torque, or the one of the tension in the belt is given, if you have to find the force in the belt, and then you can find the torque based on that. But as we have explained in this slide, and also this same problem we have uploaded in the classroom. Now the normal force, which is we generally call as driving force, is on the belt, is nothing but torque on the pulley divided by the radius of the pulley. You know that torque is F into R, Fr sine theta, where maximum torque is Fr, where sine theta equals to 1. So from that the force will be T over R. So in this case, because we have the pulley receiving the full power, that is 20 horsepower, so its torque is 570.2, as we have calculated before. Now we can find this is the driving force, and driving force is calculated by torque over radius. And remember, this diameter is the pitch diameter of pulley. And by the way, there is no need to go into the depth. Whenever diameter is given in those problems, in these particular problems, always take as the pitch diameters. Clear? But generally, if you remember from probably from your previous last 2 years of your engineering, you probably have differentiated between the outer diameter and the pitch diameter. Pitch diameter is generally called the effective diameter, the diameter where forces are actually applied. So the normal force, we know this is 570.2, clear, divided by, so you know D is diameter of pulley is known from the problem, and that is 35 centimeter. So when converting it to meters, we call it 0.35 divided by 2. Clear? So value come out to be 3258.3 Newton. Clear? So the normal force is calculated for the belt. Now for the V belt, we know that bending force is almost 1.5 times the normal force. So the bending force is 1.5 times 3258.3 Newton, and that value come out to be 4887.4 Newton. Clear? So from that we now know that FBH is equals to FB, and the horizontal component is the sine component, sine of theta. Sorry. The horizontal component is the cos of theta. So cos of theta. So 4887.4 into cos of the angle of the belt, which is 45 degrees. So the value come out to be 3455.1 Newton. Similarly, the vertical force is FB sine of theta, and that is 4887.4 into sine of 45 degrees. That value come out to be with the 45 degrees, the value is same. It's 3455.1 Newton. It could be different if the angle is different, because the sine 45 and cos 45 will have the same value. So the forces in both vertical and horizontal plane are equal. Similarly, finding the WT and WR, we know that WT is the tangential force, which is the driving force of the gear. That will be equals to the torque on the gear divided by the pitch diameter of the gear. Here again I am repeating, pitch diameter means effective diameter. It's the diameter where the two gears, the two teeth actually made. So this is the, let's say if a gear like this, so this diameter is called the pitch diameter, actually with the mating point at which the load is applied. So generally in the exam, if the diameter is given, that take it as a pitch diameter. So the tangential force is actually the driving force of the gear. So now we know, because there is only one element, so all of the torque is actually this, because the shaft is same, so RPM is same. Always remember, because we have mounted the pulley and the gear on the same shaft, so both will experience same RPM, which means both will have the same torque, unless there is another element which is consuming certain amount of power. Then you have to find the torque on one gear or the torque in the other element. Okay, in this case we only one gear, so we have TG, which is same as TP, because we have one power receiving element and one power transmitting element. So it's 570.2 divided by, and now the diameter of the gear is 25 centimeter as given the problem. So it's 0.25 divided by 2. So the tangential force is 4561.6 Newton, and from the triangle, this triangle, we know that VR is Vn into tan of theta. Sorry, VR is equals to Vt tan of theta from this triangle. So VR is equals to W, not V, sorry, I'm again thought it's W, it's a load, sine phi, where phi is the pressure angle of the, tan phi. I'm just to eliminate any confusion, I'll just draw it again. This is the Wn, this is Wr, this is Wt, and this is phi. So Wr is equals to Wt tan of phi, where phi is the pressure angle of the gear, and that is the equals to 20 degree as given in the problem. So 4561.6 into tan of 20 degrees. That value come out to be 1660.3 Newton. Now I will just import the diagram again. just to write those values. There's no need to do that in exam, just for the sake of understanding. So WR has found out to be 1660.3. The FBV is 3455.1. Similarly, WT is 4561.6, and FBH is 3455.1. Clear? So 4 forces are now known. Now we have to find the reactions. If you find the maximum bending moments, you have to find the reactions. For reactions, we know again from the classical understanding of the statics and mechanics, the mechanics of material again. You have to take summation of forces and then summation of moments. So let's start with the vertical plane. So in vertical plane, taking upward as positive, so it's a minus RVB1, which is the reaction of the vertical reaction on bearing 1, minus RVB2, which is the vertical reaction of bearing 2, plus 1660.3 plus 34551.1 equals to 0. So we know that RVB1 plus RVB2, that is equals to 5115.4 Newton. And for finding these forces, if I take moment, summation of all the moments at point B1 equals to 0, by taking clockwise as positive. You can take any, you can also take counterclockwise as positive. So just take counterclockwise as positive, just use tradition. So take counterclockwise as positive. So see MB, take down this point. So this is the clockwise moment due to this force is clockwise. So minus 1660.3 into distance is 100 millimeter, which is 0.1 meter. Clear? This is first moment. The second moment is, so this is anti-clockwise, so plus 3455.1 into 200, which is 0.2. And the moment, this moment is again clockwise, minus RVB2 into 0.2 plus 0.15, which is 0.35, and that is equals to 0. Clear? 34551 into 2 minus 160 into 100. Okay. So if you solve this equation, and I think so you can solve it from your previous understanding, RVB2 comes out to be 1500 Newton. And from that you know that RVB1 is 5115.4 minus 1500. So answer come out to be 3614.5 Newton. Clear? So let's take the vertical plane, so horizontal plane. Okay, I'm just doing it here so that you have a diagram in view. so that you can easily draw all these forces and moments. So the horizontal forces you also find. Okay, so let's start again with the prediction of taking upward forces positive. So the minus RHB1 minus RHB2 plus 4561.1 plus 3455.1 equals to 0. So we know that RHB1 plus RHB2, that is equals to, if you add both forces, that is 8016.7 Newton. Okay. So now taking the moments at B1, again to the anti-clockwise positive equals to 0. Now finding these moments, and again this is that you've done previously in kinds of materials, frequent times, number of times. Clear? So just take a moment about this point. So this is clockwise, so minus 4561.6 into 0.1, clockwise, so it's taken as negative. This is also, so this is anti-clockwise, plus 3455.1 into 0.2. Distance is given, moment arm is given, and this is again clockwise, minus RHB2 into 0.35 equals to 0. So from this we know, just writing here, from this we know that RB H2 equals to 671 Newton. And from this equation now, we can find RHB1. So RHB1 is 7345.7 Newton. So see, we have find all these forces. And just for the sake of your understanding, I am again importing the same diagram. In the exam, you don't have to import it again, just go back and write the forces. So I'm just imported in again and just again writing all those values. So in the black we have the action forces, which is 1660.3, 3455.1, 4561.6, 3455.1, and from the right we write the reaction forces, which is RH. Okay, RVB1 is 3614.5, 3614.5. RVB2 is 1500. RHB2 is 671, and RHB1 is 7345.7. 7345.7. So see, I will find out all the values, and in the exam you have to do the same technique, same procedure to find all these forces on the lower diagram. Now you have to find the bending moments, and always remember that bending moments at end points are 0 whether there is a bearing or any element. There is no bending moment at both the ends of the shafts. Clear? So in vertical plane, bending moment at B1 is this force into this distance, this force into this distance. Clear? So sorry, just so not the case. This force into this distance is the bending moment at this point. Okay? So bending moment at B1 in vertical plane is 1660.3 into 0.1, and if you want to take the direction, so this is the clockwise, which is taken as negative. So take anti-clockwise as positive. This value will come out to be 166.03 Newton meter with the minus sign. Clear? And the bending moment at P is this force into this direction. Clear? This force into this force. So bending moment at this point is this force into this direction. Clear? So 1500 into 0.15. So value will come out to be minus 225 Newton, plus Newton meter. So this is a tradition in the designing that at both ends of the shafts, at free ends, edges of the shafts, the bending moments are considered as 0. So only the bending moments at the midpoints are considered. Whether there are 2 points, we have 2 moments. Whether it's not necessarily that the bearing or the element, whatever are those elements, either bearings or the counter-arithmetic elements, the bending moments have a certain value at the midpoints, and at the edges of the shaft they have the bending, has no bending moment. Okay, so you see, in the horizontal plane here, the bending moment at B1 is equals to 4561 into this. So 4561.6 into 0.1, which is, and because the clockwise direction, so anti-clockwise is taken as positive, this must be negative. So 456.2 Newton meter. Similarly, bending moment at P is this load into this distance, which is 671 into 0.15. So 671 into is 100.65, or I call it Newton meter, and with a plus sign. This is with a minus sign, this is with a plus sign. And again, the bending moments at both edges are 0. Now, as I mentioned, there is no need to draw the shape for the bending moment diagrams, although you can draw it for both planes, as you have understood in your mechanics of material course. But in the exam, there is no need, because again it takes time to draw it. We just need to find the diameters. So before going that, we have to just find the resultant bending moments at B1. So B bending moment R at B1 is equal to bending moment bending moment in just find the bending moment at both points. So bending moment at B1 is the bending moment B1H plus bending moment B1V. You see, bending moment in horizontal plane at B1 is minus 456.2 square plus bending moment in vertical plane is minus 166.03 square. See, the resulting bending moment at location B1 is 485.43 Newton meter. So minus sign is actually dissolved in the square. So there will be no minus here. Similarly, based on this diagram, the bending moment at P is the bending moment at PH plus bending moment at PV square. Now, horizontal component, the bending moment at pulley is 100.65 square plus bending moment in the horizontal plane, vertical plane is 225 square. So value will come out to be 246.49 Newton meter. Clear? So here find the resultant bending moments at both points, at B1 and at P, which are the 2 points on the pulley excluding the end points. Clear? I'm again repeating. In case of the shafts, it's a tradition that we do not have to take any bending moment at the edges. So only bending moment is taken inside those points. Clear? Either 2 points or 3 points. In some problem there will be 2 points, in some problem there will be 3 points. Now in the start of the problem it is given that find the design the step shaft, which means that find the diameter at every shaft, at every point. See? So we know from the formula which will be given in your exam, that is, and also given in the slides, 16 over pi tau allowable is moment square plus torque square. So at each location, so just in the case of I want to calculate for the one particular okay, so for one particular location, that is the location at B1, just want to find the diameter. So just I'm putting this value. The tau allowable as from the very start is 146.5, which is the lowest value. So 146.5 into 10 to the power 6. Of course, we'll convert all these into meters. Square root. This is basically bending moment square. And bending moment is the resultant bending moment at that particular location. So resultant bending moment is 485.43. So that is 485.43 square plus the torque on that particular element, and we know from that is 570.2. Clear? So at this point the diameter has come out to be 0.00, okay, not 0.0296 meter, that is 29.6 millimeter. Clear? Now if you want to find diameter at location G, which is the edge of the shaft, so then you know at this point bending moment is 0. So your formula will come out to be cube root of 16 over pi tau allowable and only t, because bending moment will be 0. This is cancelled with this, you get only t here. This is the basic formula that we have done in the class number of times. So let's say in case of this, it will come out to be 0.0271 meter, which is 27.1 millimeter. Clear? And also in case of P, within the same bending moments, this value will come out to be 0.0278 meter. That is 27.8 millimeter. Again, remember at location, at diameter of at the diameter where pulley is located, just use the bending moment of the pulley. And at the last, which is B2, where there is again the edge point, there is no bending moment, diameters come out to be again the same, which is 0.0271 meter, which is 27.1 millimeter. Clear? But in some problem there could be a possibility that it is written find the it is not mentioned find the step, design a shaft. It is written design a shaft. So in those particular, when the step word is not used, you have to design the shaft based on maximum bending moment. I'm again repeating. So see, we have two bending moments. One is 485, second is 2, second is yes, second is 246. So see, if in the problem there is no indication of a step shaft, only it is meant to design a shaft. So in those particular problems, you have to take the maximum diameter of shaft. Sorry. You have to take the maximum bending moment. But if it is written design a step shaft, so it means at every point where the elements are located, you have to take that particular bending moment. But that bending moment will be the sum of the bending moment both in the horizontal plane as well as in the vertical plane. The only thing that can differ in these problems, as I mentioned earlier, is first there could be two elements that are power. There could not be two elements that are power receiving. There could be only one element that receives the power. But there is a possibility that there are two elements that are consuming those power. In those particular problems, you have to divide those power. So let's say I have a shaft, I have a gear, and that gear receives 20 horsepower, and I have a chain drive and a pulley system. So let's say this is consuming 30% of power. So let's say this is consuming, let's say 25%, let's say. So this is about 5 horsepower. This is about 15 horsepower. Clear? So now you have to calculate the torques based on the consumption of those powers. Okay? So torque will be different here and torque will be different here. Although the RPM are same, but they are using different powers. Because power is consuming, both elements consume different amount of power. Although the RPM are same, because they are mounted on the same shafts and there is no relative motion between elements, but the power consumption is different. And one thing we need to mention, in case of chain sprocket mechanism, the bending force, we call it FC, which is the chain force. It also has two sides, but it's called the tight side of the chain, second or slack side of the chain. But in case of the chains, the slack side tension is 0. If you have just observed the running of a chain on a sprocket, you see the loose side has almost, if you can feel it, it is under tension. But in case of belt is under tension. And in case of chain sprocket mechanism, the only difference is there will be no force on the slack side, so the driving force will be T over D by 2, and that same force is the bending force on the shaft. So in case of sprockets, the analysis become much more simpler, and only the FC, which is the chain force, is considered. That can be calculated by torque on that sprocket divided by the pitch radius of that sprocket. And if it is at certain angle, so definitely if the belt is exactly horizontal, so like in this, so we have only horizontal component, there will be no vertical component. But if the chain or belt is at certain angle and the angle is well known, like 30 degree or whatever that is, then definitely we have two forces, one is horizontal and one is vertical. And again we have to draw the in both these planes. Clear? So I hope that from this solution of this problem you have understood the design of shafts. I've actually discussed all the cases which could be possible. I will try to upload another problem that you can practice so that you will have more comprehension of the topic. So thank you very much for your time. If you have any questions, you can actually consult with me on Thursday and Friday in my office. Thank you very much for your time. Allah Hafiz.